Okay, good. Welcome back. I was hoping there to have all these lessons in one complete video again. Case for today anyway. Trying to do this recording. So let's get into it. Perhaps it may be good. At least you get to get up like me and to get some water, or just to be a bit more comfortable anyway. Right, saying that the issues with the LEV system, you can get the shortcoming with, for example, the hoods, the position, the ductwork possibly being square, fan speed. Those would normally be the reason, the local role of contaminants. So the LEV hood, correctly called the local exhaust ventilation hood. This is the point where contaminated air is drawn into the ventilation system. The sizes are for specific task or situation. So if you want to explain some of this, the airspeed velocity of the hood opening and inside the hood must be enough to catch or capture and carry the contaminants or the contaminated air in. So there is actually something called the Captor velocity, and what that really is that simply saying the speed of air is great enough to suck those contaminants in, right? But some of those terms anyway, I guess as you go through your handout, you have to use the proper terms. This Captor velocity must be enough to catch or capture and carry the contaminants in. There's actually something called the transport velocity as well, which is the once inside the hood, it will be able to carry the contaminants into the hood. Right, I think I'm right there. Right. So to be most effective, the hood should surround or enclose the source of contaminant, or be placed as close to the source as possible. The three common classes of hoods are enclosing, receiving, capturing. Hood should be designed to confine or enclose the contaminant whenever possible, as for inspection and maintenance. So this is a very critical point for exam. What do you consider in selecting a hood? For example, like an employer. So you must consider things like can they get access to it for maintenance, and how often would it need to be inspected after the initial installation. So those are points employers would normally want to consider before selecting an LEV system. Capture hoods are used to capture contaminants that would not naturally move into the inlet of the system. Whenever possible, flanges should be provided on hoods to eliminate the tendency of drawing air from behind the hood. So what is a flange? You'll pick it up on this slide here. Flanges improve the effectiveness of capture hoods. As a general rule, the width of the flange around the hood is equal to the hood's diameter or one side, but should not exceed 150 millimeters. So not really much of that there for exam, but the flanges are basically these the end part of the hood. If you have a vacuum cleaner, I guess maybe a car vacuum, it would be like the harder part connected to the flexible hose itself, and what that does, it does to be drawn into it, and the flange, if it's good enough, right? Hood design, types of hood: enclosing hood or fume hoods are hoods surrounding the processor points where the contaminants are generated. Examples of completely enclosed hoods, all side enclosed, are glove boxes and grinder hoods. So you may have been familiar with that. To get your hand inside of it, you'd have to put your hand into the glove. That's an example of a totally enclosed hood. Or spray paint spray boots. The enclosed hood is preferred whenever possible. So this here would have been an enclosed hood. Receiving hoods is actually emission from a source that is, for example, a type of receiving hood called poison air and gases are shown in figure 2 in the next slide. An exit located in furnace would be an example. So again, all of these have to learn the type of hoods. So this is a receiving hood. Contaminant rising from hot processes would be captured by this canopy hood. Generally, one or two of the names are sufficient for exam. Capturing hood. These hoods are located next to an emission source without surrounding or enclosing it. Examples are a rectangular hood along the edge of a tank. Examples include most common industrial LEVs. So again, just a point of interest here, most LEVs would have this type of hood anyway. So as you see, typical for most LEVs in the workplace, the process is taking place here, and then the canopy would have been just above it. Types of Captor hoods: slots, flange, slot, plain opening, flange opening, boot, or canopy. Right, let's continue again with the LEV system. Just need to line up the slides for you all again. So we want this particular slide. Types of Captor hoods. Again, an idea would have been to learn some of these. Perhaps some of the better ones would have been canopy, flange. Really just about 2 to 3 for exam would be quite sufficient anyway. Right? On your handout, not too sure if you can make all of these out. Again, the idea is that it's not really a drawing exam, but just to know the names. Canopy has appeared in past papers before. Flange, boot hood, all of those would just be sufficient for your exam. Right, so I'd mentioned this term before. This is the capture velocity of the air. Let's read it out first and then see if you still need any explanation on it. It's quite the same, that that the air at the face of the hood must be somewhat like a vacuum. It must be enough to pull the contaminants into the hood itself. So the ventilation system removes contaminants by pulling from the worker or the source. Airflow towards the hood opening must be fast or high enough to catch and transport the contaminant until it reaches the hood and ducts. The required airspeed is called the capture velocity. As much as possible, the other sources of air motion should be minimized or eliminated for the ventilation system to work properly. Common sources of external air movement includes thermal air current, especially from hot processes or heat generating operations, motion of machinery such as grinding wheels, belt conveyors, etc., material motion such as dumping or filling, movement of the operator, room air current, which are usually considered 50 feet per minute, but may be much higher. Rapid air movement caused by spot cooling and heating equipment. So again, if you see me looking down, I'm trying to see the timer and the microphone is still working at the same time. So what was this all about? In addition to just talking about capture velocity, this again has come for exams before. It would have been, what are the competing systems for the capture velocity? Simply saying that the vacuum then of the hood, the air pressure that capture must be great enough to overcome all of these competing movements of air within a room. So you may have thermal air current. The very fact that an employee may walk creates a disruption to the airflow, right? So you have your movement of the operator, room air current, especially if you have fans in the room in addition to the LEV system. All of those are competing systems for the suction in the LEV system anyway. So quite a nice concept here if you got it, that the capture velocity has to be greater than all of these competing systems for the contaminants, so that the capture velocity must be large enough to overcome all of these competitors anyway, to get the contaminant into the duct of the LEV system. So I guess a graphical representation here. This may be the hot process taking place. This is the hood and the position of the hood, but then you have You may have a fan, you have an open window, you have an open doorway. 10 to 1, I mean, hot air tends to rise. So the Captor here at this hood needs to be greater than all of these. It needs to be enough to pull these contaminants without the fan, I guess, blowing that to the other side of the room, as well as to the window and the door, right? So a nice concept there for exam. What are the ways, I guess, a LEV system could be ineffective? I guess in addition to the hood maybe being poorly positioned, you could have competing sources of air then, or air movement within the room that may disrupt the flow of contaminants from the process to the LEV system. So general hood designs, you could have a read of this, just an idea here, right, of the type of pressure of air that is needed, or the type of airflow. You say if you would, of course, move the hood away. If a hood is moved from 2 inches away from a source to 4 inches away, twice the distance, the airflow required to put in there. So I was just saying that you do need to have competing sources of air, as well as even distance. If you move a certain distance, move the LEV system away from this thing, the airflow. Alright, let's go again. Let's try to set this up. Right, phase velocities. Again, exactly what the note says here. Phase velocity is the velocity at the mouth of the hood, and again, the idea here before I read this is that the Captor velocity has to be greater than the phase velocity. So phase velocity used as a standard for assessing the effectiveness of the LEV system by comparing the velocity of air at the opening or the face to that of the airflow throughout the system. Airspeed at the inlet or outlet of the LEV system. Phase velocities can be obtained by taking measurements at various points and plotting the values on a grid of the face area. An average or mean can then be calculated. Phase velocity is the airspeed at the face of the hood, calculated by dividing the airspeed by the total area square footage used. An example would be air is measured using an anemometer to give a reading of 1 meter per second, 2 meter per second, or 3 meter per second. Given the area to be worked in is 15 by 20 by 8. 15 by 20 by 8 room, calculate the phase velocity. So the answer will be, you will take the initial movement of air. The movement of air is measured in meters per second. Speed, of course, is meters per second, so it's the same thing anyway, the same units. So 1 plus 2 plus 3 will give you a total of 1 and 2 there, 3 and 3, 6, divided by the total area of the room. So the 15 by 20 by 8, 2400, 6 divided by 2400, 0.0025. As such, the Captor velocity must be greater than the phase velocity of 0.025 meters per second squared as to draw the contaminants inside the hood. Transport velocity of air, again, mentioned this just a while ago, that this is once inside of the hood, the speed of the air needs to be sufficient to carry the contaminants along the entire docking of the hood. And again, if it's not, it could result in contaminants settling on the corners of the LEV system, settling perhaps on the fans, etc. So this is the minimum velocity to move the contaminants already in the airstream the required distance through the system. If not, particles will fall out of the airstream. As such, velocity should be high enough to prevent settlement of the contaminant particles. Transport velocity should also not be too high to increase the fan power and consumption. It's not to overrun the system so that you overrun the fan and the power as well, but to set it at that speed then that the contaminants can move fluidly through the system or freely through the system and be filtered and exhaust back to the atmosphere. Transport velocity is measured at a number of points in the system by taking measurements inside the system docking with the system operating. Can be measured using an anemometer, and you may want to learn that. Various types are available: swinging vane, rotating vane, digital and analog anemometers. So you can probably learn 1 or 2 of them. I've never really seen a question asking how they work. You'll see them at the end of the slide. The digital, of course, is the easiest. You put it on and give you the speed of the air in meters per second. The swinging vane normally has like a swinging pointer, like a clock, and again that will swing with the movement of the air, at which time will settle on a particular reading. So there's a couple of diagrams on this presentation that you could look at. Again, there's no diagrams for exam, it's just to know that, you know, if they had to ask how do you measure transport velocity or even capture velocity, you can simply say by the use of anemometer, and if you're able to give a name, digital of course being the simplest in today's age, that will be sufficient. So air cleaners are on, I suppose, another part of the LEV system. So we'd have looked at the hood as well as the face. We would have also looked at the competing systems for air or contaminants as they are to be drawn into the hood itself. So common type of filters, again, this would be really what cleans the airstream. So type of filters depend on the contaminant. Design of filters must not limit the capture velocity or transport velocity of the LEV system, meaning that the filter shouldn't put extra strain on the system. It should be of a suitable, you know, pore size and whatever have you. Example, an acidic exhaust mist may require alkaline scrubbers to neutralize the acidic properties of the mist. Typical examples of filters or air cleaners include wet scrubbers, fabric filters, cyclone filters, electrostatic precipitators. So these are quite good. What we have been seeing for exam though is that, well, they do like this one here where they would have mentioned some acidic solution, and they would have suggested what type of, you know, like what could have caused the system not to filter it, and you know, or cause the system not to be effective. And they were expecting the students to suggest something like, you know, acidic filters had to be neutralized with an alkaline scrubber. And again, that is what would be the knowledge, you know, base of that anyway, not to draw and label these things anyway, right? So I guess a good idea is to learn some types of the scrubbers. So I have some here, air cleaners or wet scrubbers. And a wet scrubber, the polluted airstream is brought in contact with the scrubbing liquid by spraying it with the liquid, by forcing it through a pool of liquid so as to remove the pollutant. Scrubbing liquid can be alkaline in nature if source of contaminant is acidic. Again, maybe a kind of blurred picture if you have never seen a scrubber in real life. You know, again, for those who know me from way back when, did spend some of my early days around, you know, ones that look very much like the one on the right hand side of my screen here. Wet scrubbers, effective with hot gases, corrosive, eliminates explosion hazard. Limitation includes noise, corrosion, biological fouling, not an issue in caustic or acid scrubbers may also occur. So biological fouling may also occur, right? It may actually pose a bit of a tripping hazard or slipping hazard if the system is a bit leaky, right? You know, electrostatic precipitators. To those who have never done this one, I'll just run through this one. So here you have in the LEV itself, there will be a charge plate. Normally these plates would be positively charged, and they would run or pass an air current through the LEV system. That of course current is negatively charged, so the contaminants in the airstream will pick up that negative charge and it will be attracted to the positive plates. And these are normally pieces of iron anyway in the filter system that the negatively charged contaminant will actually be attracted to the positive plate, kind of like, you know, I guess like flies to honey anyway. And at the end of the day, what they do is that they will take off these plates and normally wash them out. So it's a way of, you know, getting the negative to attract so that the contaminants are attracted to the plates anyway. So an electrostatic precipitator is a filtration device that removes fine particles like dust and smoke from a flowing gas using the force of an induced electrostatic charge, minimally impeding the flow of gases through the unit. Effective in high temperature and corrosive condition, high cost, as I mentioned, the current flow there and the cost of washing of those plates at the end of the day, setting it back again. Large equipment requires specialist maintenance. And again, that example, as I mentioned, at the end of the day would have been for small systems. I suppose you can only imagine for bigger systems that it may be at the end of the month by a skilled technician, which may be a bit of a cost as well. Right? Ductwork should be of an appropriate size, and this is the lagging, as they would call the silver pipes of the LEV system. Should be of an appropriate size to allow for sufficient transport velocity. Should be sufficiently strong, well supported, and capable of withstanding normal wear and tear. The number of changes of direction should be kept at a minimum. Should be made smoothly with rounded bends. Access to ducting may be required for testing and maintenance. So again, these are some of the main features of the ductwork itself. It must be of an appropriate size. For example, they do like the idea about it, being round and having limited bends, so as to allow the free movement of contaminants through it anyway, right? So ductwork, the construction and material of construction needs to be compatible with the contaminant being extracted. For example, where flammable gases or vapors are being extracted, the system should not be able to generate a source of ignition. The ducting needs to be structured so as to avoid eddy current and inefficient flow. And you normally will get those around where you have the sharp bends anyway, right? For example, it should not have sharp right angle turns, as this leads to dead areas with no airflow. Ductwork likely ignition sources could arise from the use of non-rated electrical equipment such as the air mover, or from the accumulation of static electricity from the lack of earthing and bonding and the use of non-conductive materials. Corrosion by the contaminant is possible, and again, that's simple. In Trinidad here, we would have had past fires where the amount of dust, for example, there was one at KFC in Mayaro, the amount of dust and oil that would have accumulated in the LEV system would have been what would have, kept a fire going once a fire would have gotten started in the kitchen area of KFC. There was another one I know at Grand Bazaar as well. So that these ducting, if they are not inspected, not the proper tools being used and stuff, they could be a source of contaminant, for example, oil, dust, corrosion, etc. And then that may just be sufficient fuel to keep a fire going, right? So some pitches with rounded bends, testing the ductwork for sufficient transport velocity with an anemometer. I do have also some videos that I guess I would have to put up on YouTube as well. These would of course not be my videos, but so I hope we have the free rights, use of YouTube videos. So I'll probably post those as well once I get this recorded of today's Sunday, of course, by Monday, so you can have a look at it. Right? Local exhaust ventilation system, just an idea of one there. So again, air movers or fans. So we looked at the type of hoods. Really coming out of that, you need to know just about two types of hoods. Canopy, boot would have been very, very famous. We looked at the type of filters just on the last couple of slides. To know that there are stuff, the type of filters called scrubbers and electrostatic precipitators and alkaline filters, etc. We also looked at the shape of the ducting materials. The features of that must be round, sufficient size, robust enough to withstand, the source of contaminant that it has to extract. So I guess almost last here you have fans, the type of fans, and again you just need to know about two types of fans. So the fan can be of a number of types. Centrifugal, most commonly used for LEV systems, generate large pressure differences and produces airflow against considerable resistance. Propeller, more often used for general ventilation and usually not suitable where there is pressure resistance, for example, in a line. So you could probably go with centrifugal. They have actually seen that one, and this one here, axial, not suitable for dust and cannot overcome pressure resistance. Pressure air driven compressed air driven air movers can be used for specific tasks. where electrically powered fans are unsuitable or where they are flammable. Running costs, low performance rates, and high noise levels. Can't remember that. I know they had asked about 2 types of fans for the LEV system. So I think coming out of that, I would have done this slide, centrifugal and axial, and maybe some of the advantages and disadvantages of them anyway. Types of fans: centrifugal fans, forward curved, advantage, large air volume against low pressure, relatively small size, low noise level. Disadvantage: not high pressure, harsh service, difficult to adjust fan output, careful driver selection, low energy efficiency of these centrifugal fans. Again, this is maybe something to perhaps find that past paper and get some advantages and disadvantages of the 2 types of fans. I wonder if I'm on the correct slide here. Yes, it seems to be. Engineering controls measures include dilute ventilation, local exhaust ventilation, guidance here, HSG 37, HSG 54. Looking at the further reading material that you'll need to get as well. Right. Moving along, factors to reduce the LEV effectiveness. So we mentioned some of this before. Perhaps a draft in the workroom, poor hood design, greater distance of the LEV effectiveness relies on the placement of the inlet very close to the source of contaminant. Damaged docking can lead to leaks, which may hinder the transport velocity. Leaving too many inlet ports open can lead to a loss of suction. Unauthorized alterations such as additional docking or modifications. Process change such as an overwhelming amount of contamination at a previous Captor velocity. Changes in the fan strength can lead to dust falling or being deposited in the docking. Too many sharp bends are blocked or defective filters. Dilute ventilation, again there was a question on this in the recent couple of years. Straight up the question that asks a lot about dilute ventilation. So again, if I get time after this, I'll probably try to find that past paper. Again, I mean, just about one anyway, but again, the advice would be for you to find, all and give them a try. So dilute ventilation involves using natural air movement through doors and windows or using mechanical air movement to dilute any contaminated air, hence reducing or eliminating the airborne pollutant. Not suitable for toxic substances in the breathing zone of the employee. An example can include general air conditioning provided in an office environment. So as I click this one here, I remember the question would have been like, when would dilute ventilation be suitable? So it should only be used when non-toxic contaminants or vapors that is easily suspended in the workplace air, not dust. Small known quantities of contaminants is produced. There is no defined point of release of the contaminant. No other practical means of reducing the level. Dilute ventilation is often used to maintain a good working environment, enabling fresh, clean air to be provided at a suitable temperature and humidity for comfort. So when they use dilute ventilation, straight from this slide, right, the source of contaminant is it's not dust, right? Perhaps whatever it is, it's of known quantities of contaminant, no defined point of release, no other practical means of reducing levels. So I actually don't have my book with me today, Sunday, left it at the office on Friday. So you can check that up a bit. It's in your book. Perhaps in the next video I will get my book and I'll be able to give you the precise page. Inspection and maintenance, I'll just talk you through this one. So you would have remembered in the very first slide, which would be on the other video though, that we mentioned that this is in compliance with the COSHH regulations. The Control of Hazardous Substance Regulation 9 here requires that the LEV system be inspected at least once in every 14 months and every month based on the nature of the contaminant for some processes. Simply saying, if you have a lot of dust there, or there's a lot of contaminant. You may want to inspect every month based on the quantity of contaminants that is being suctioned through the LEV system. Reasons for inspection and maintenance: so to comply with the law, to comply with a workplace exposure limit, provision of information to employees, indicate the need for health surveillance, for insurance purposes, to develop an in-house exposure standard, which of course would have to be less than the workplace exposure limit. The two main things I use in inspection, these are qualitative and quantitative means of measurement. Qualitative technique uses visual inspection of the system, smoke tube tests with the system running, high intensity lamp observation for mist and dust that might be in the respirable range using tidal illumination, observation of the contamination sources and worker activities. So I just realized that my son coming upstairs there now, so you can hear me in the background, right? Just to run through this one, this one for half an hour anyway, and I have been here more than an hour because the first two videos would have had a bit of errors in it, right? Not like normally when I'm home they're often right around me anyway, so to send them downstairs would have been a bit weird, right? So just to run through the techniques for maintenance, right? So they are saying two main techniques I use: qualitative and quantitative. Qualitative uses visual inspection, and this is just putting it very simple that someone could do a visual inspection of the LEV system. They can perhaps look for things like defects. They can look at the exhaust, which is where the contaminants are coming out, to see if contaminants are really coming out. They can look at things like the quality of the filter, if they were able to dismount the filter and see what are the contaminants inside of it. Then they have an idea that the system is working or it's not working, right? For example, if you had a lot of dust in the workplace and upon careful examination of the filters, you realize the filters are clean, it's capturing those contaminants anyway, right? So the smoke tube, if you know what this one is, a lot of people in the old days would have normally used like a cigarette, for this one, but a smoke tube is something that you can buy. Trying to remember if I put it on, you simply break the end of it, sort of like a test tube anyway, and you break the end of it and a plume of smoke would come out of it. And what you do, because it's like a vacuum system, you could actually look and see if the smoke is being sucked into the hood. Then you could actually trace the smoke, right? The high intensity lamp, also called a tidal illumination, of course the picture came up here, is very similar to what you see. For example, if you were to open the windows on a morning and you see the beam of light coming in, sometimes you cannot see that amount of dust with your eyes, I guess, if you are home, but once the light is coming in, you'll actually be able to see it. So here you have an example of what it would look like under tidal illumination. And again, this may not have been apparent at first, but upon illumination you would see where the contaminants are going. So maybe a better one here would have been, yes, that these contaminants, and they pull these contaminants into the hood, right? Again, another picture here showing you that that there were contaminants around the process. So you could learn that. I need to go back. I thought there's a very interesting one there. Let me try to get this to go back a bit. So the means of qualitative testing then, right? So visual inspection, which is you just walking along the system and checking for faults, the smoke tube, the high intensity light, but also the last one is a nice one: observation of the contaminant sources and worker activities. So what that means is you could simply look at the condition of the workplace. If the LEV system was meant to extract dust, but on your work surfaces, on the benches, on the desk, on the clothes of workers, or on products you have there, it feels dusty, then it means that something is a bit wrong, right? The LEV system is not doing what it was supposed to do anyway, right? You could also probably look at the health of the workers. If a worker was coughing, complaining, right, of the area feels dusty and his eyes would have been irritated, all of those would have been qualitative means of assessing the effectiveness of the LEV system, right? Now the last two that we're going to look at, you probably would need to look it up a bit. I think that I did cover it sufficient on the slides for a NEBOSH question, but if you need any further information, you can check YouTube on it, right? I know one in particular is just funny looking one that you all see in here, and perhaps again just to know the name of it is what comes for our exam, right? So quantitative inspection can be achieved through measuring the airflow rates at the hood, dock, and exhaust to the environment. We did mention this before, using digital and analog. Just to explain this one, so if you measure at the face of the exhaust, the face of the Captor hood, and it measures 2 meters per second, you know, that velocity then should be maintained, or if not a bit higher, as it goes through the docking itself. So if it's 2 at the face of the hood, that's a Captor velocity. It would need to be a little bit more than that to transport it through the hood, especially if you have bends and wrong corners, or worse yet, sharp corners throughout the docking material of the LEV system. You'd also want to check the flow rate at the exhaust to know that the contaminant, after being filtered in the filters, the airstream is still moving back out, you know, to the atmosphere. So that can be done by the digital and the analog anemometers. And just to know that there, that to show you the point of confusion there, that velocity or flow rate is measured using the anemometers. Now there's something else you can check, something called the pressure, right? And you do not use the anemometers for pressure. You use a series of events, or a sequence of activities to find the air pressure. First of all, again, better yet, if you have a digital pressure monitoring device, that would be better. But what was covered on the syllabus, they mentioned 2 crude techniques, one of them being something called a Pitot tube, and yes, a U-tube manometer. So if you mention, I guess if you remember the name, that may be sufficient to get the marks anyway, right? So measuring static pressure in various parts of the system, and the pressure drops across the filters and the fan, could be a means of measuring the effectiveness of the LEV system. And that pressure, static pressure, it does change along the lengths of the LEV system naturally, first of all, right? Changing is not what is wrong, but if it was to drop beyond what the change would have been, indicate, you know, an ineffective LEV system. And the instruments used for that is the Pitot tube and the U-tube manometers anyway. So a U-tube manometer contains water, oil, or some other appropriate liquid that is displaced when pressure differentials in the LEV system are found. That is when a tube is connected to one or both ends of the U-tube manometer. Static pressure, velocity pressure, and or total pressure can be measured in inches water gauge, or inches of water gauge. So this, of course, I said would have been a very... What you need to appreciate here is that exactly what they say it is, it actually is. One end of it is connected to, you know, they'll have to drill a hole and put in this hose anyway, right? But one end of it is connected to some part of the LEV system, right? And so, you know, connected to one or both ends of the U-tube manometer. So one end is connected to the manometer, the other end, of course, you know, one or both ends of the U-tube manometer. Now, typically, I was saying one end is connected, and the reason as the other is connected to a supply of water, right? Which you're not able to see in this picture here, but the pressure difference then, again, if I come back to my water bottle, I guess, the pressure difference is able to displace the water, right, that you're not seeing in the picture there, and the water that is displaced is a measure of the pressure that was in the system, right? So if you want to go that technical way, you just learned the note before, right? You know, you could mention the name of it. Of course, I said today you have more or less digital air pressure meters or manometers that is used to measure differential pressure, right? So let's move on there. So the Pitot tube, again, this is a crude piece of instrument, really being just a piece of metal. It's like two pieces of metal, piece of a metal inside of a piece of a metal. And when I say a piece of a metal, about you know, thin as a pencil, right? But like two columns inside there is a very crude version of a Pitot tube. So this is a pressure measuring instrument used to measure fluid flow velocity. The Pitot tube was invented by the French engineer Henri Pitot in the early 18th century, used to measure static pressure in the LEV. They are inexpensive and robust. As I mentioned, they would have been like a piece of metal and typically just steel anyway. Tubes do not require calibration, can measure above 3 meters per second, such as wood dust produce some circular saw cuttings. So again, to me, all of these are not the technical details of how they work, is not what is needed, but just to know that the names of them are there. Pitot tube, U-tube, manometer, used to measure pressure. Static pressure is the air pressure inside the LEV system. It is air inside the LEV system that presses on the walls of the LEV. So as one of the slides had, and I don't want to go quite back, but as one of the slides have, what they use to measure the effectiveness of the LEV system, it would have been, let's try to get back to that slide, but it would have been static pressure. They mentioned that word before. Then we have passed it here, static pressure, and the velocity, right? So static pressure, we have missed it a bit, right? So this would have been trying to get this back for you. So this one would have talked about the velocity, right? But spoke about the pressure, right? So right, so this is it. So measuring airflow rate by the anemometer, and then you see static pressure. So we have used the word kind of haphazardly before, but static pressure is really something. It is the force of the air that's acting on the inside of the LEV system, and this Pitot tube, right, is able to measure that static pressure, or is able, in fact, I guess the crude version of it is really not able to measure static pressure. Is actually able to give you two readings which you can use to manipulate to find the static pressure. I suppose but as you go back to this slide now, you would see to get the static pressure you actually have to do a bit of calculation. So in a way, the Pitot tube is not quite giving you the exact static pressure, but it's giving you a reading that you could minus, right, and that would give you the static pressure anyway. Of course, I could tell you right here. Let me just go back to the slides and see if we can get it from off there. Right, so static pressure is the air pressure inside the LEV system. It is the air inside the LEV system that presses on the wall of the LEV. Right, so static pressure can be measured using a manometer to measure the absolute pressure inside the system. So what you really get is the absolute pressure, and what you do then, you compare it with the atmospheric pressure to determine the difference, which is difference, of course, means the minus. Now we should probably know that atmospheric pressure has standard value. It's given as 1 atm. Alright, so I say that again, atmospheric pressure in most systems and is given a constant figure, which is 1 atmosphere, right? So if you were able to get the absolute pressure in the system, for example, let's say the absolute pressure is the number 2, then to get the static pressure, you find the difference between the absolute pressure, right, minusing the atmospheric pressure. And what you'll get there is the static pressure, right? So the difference is called the static pressure. So then 2 minus 1 will give, of course, giving you back 1. This information is useful, is a useful indicator of how much negative pressure the fans are creating and how effective they will be at drawing fresh air through the hood. Now again, this is another concept that we mentioned here, that this you must know that suction then, which would have been what is needed, suction, what is needed at the hood, right, of the LEV system. Suction is what you call negative pressure, right? Negative pressure pulls air in. For example, again, a vacuum operates on negative pressure. If you have air that is being expelled, that's called positive pressure, right? Again, I don't think any of these are really exam points anyway, but just to know them, right? So I repeat it again, negative pressure pulls contaminants in, or negative pressure creates suction, right? Positive pressure creates push, like you find in an AC unit. An AC unit works on what is called positive pressure. You can put your hand and you'll know that the air is hitting your hand. It's not being sucked, it's being, expelled upon your hand. So what I'm trying to get here with, do I get a bit of calculations, is that if you had to measure the static pressure at the hood of an LEV, it must have been a minus figure, right, for it to be a suction or negative pressure. So using the manometer, again the screwed version that they mentioned here, if you measure the absolute pressure with the Pitot tube anyway, inside of an LEV system, and this would be before the fan. Say before the fan, of course I do have my marker here now, but before the fan, you have to have what is called negative pressure to create suction. This is the fan inside of the LEV system. After the fan, you have to have push, to push the contaminants, or to keep pushing them out of the LEV system to the atmosphere. So after the fan, you also have to static pressure, but it needs to be positive anyway to create that particular push. Let me see what I put on this slide here for you all, right? So low static pressure can indicate that there is not enough suction in the LEV system to draw the contaminants in. Too high static pressure can also indicate, let me just go back with this. Too high static pressure can also indicate that there is not enough inlets in the LEV system. Before the fan side of the LEV system, the absolute pressure is lower than the atmospheric pressure. As such, the static pressure is always negative to create the suction needed. I was saying this before when I thought that I had put something in the slide here on it. If you did measure, I'm looking at the time, I have 10 minutes on this presentation. Again, the hour is almost up. So yeah, if you did measure the absolute pressure on the first part of the LEV system before the fan, it had to be smaller than 1. The figure had to be lower than 1. So let's just say 0.5. The reason is that when you minus it, remember atmospheric pressure is 1. So if we say 0.5 minus 1, absolute pressure minus atmospheric pressure, 0.5 minus 1, right? Let me see if I get it right. I've seen people use this anyway. So then you'll see that it will be, I don't know how much you can see of that there, because I can't see it myself, right? But I guess yeah, 0.5 minus 1 would have given you minus 0.5. So, you know, probably use a pen though. So minus 0.5 would be negative. So negative pressure is what creates the suction, right? So that's the idea. Though again, I've never really seen that on a passive press. I'm just trying to do my best, you know, to break it down so that you would understand it, right? I went a bit too fast there. Let's try to go back this presentation. So on the 9 minutes remaining, the exhaust side of the LEV, the absolute pressure is higher than the atmospheric pressure. As such, the static pressure is positive to produce the push needed to exhaust the air to the outside environment. So again, if you measure on the the pad after the fan would have been, let's say, about 4, right? So you get like 4 meters per second. I may be giving you the wrong units there because pressure is not second. It could be, I suppose, in pascals or something else anyway, right? But it'll be 4 anyway, so 4 minus 1 will give you 3 again. 3 is a positive number. It's not a negative number, and that will create the push needed to exhaust the air to the outside environment, right? I may be overdoing it on this explanation, but again, the idea I'm trying to remember how this came, can't remember much of it. It would have just been what is the instrument used to measure pressure. Students would have confused it, of course, with the anemometer, which is really airflow. Pressure is really the Pitot tube and the U-tube manometer anyway, right? Instruments are measuring air velocity, hot wire anemometer, so I just said it here, swinging vane anemometer, rotating vane anemometer. Hot wire anemometer measures the air velocity by noting the heat reduction in the heated up wire or core of the instrument. Time taken for wire to cool can be converted into the air velocity. Swinging vane anemometer uses a hinge vane that swings with the movement of air. A movement on a pointer across a scale can give a measure of the air velocity, right? So instruments are measuring velocity, rotating vane. Rotating vane anemometers have been around for many years. Rotating vane anemometers are very sensitive low pressure or low velocity instruments. Most modern ones today are capable of air velocity calculations or direct reading. So pretty straightforward here. And just to end this here, we have an extract of the COSHH regulation. What is the the objective of the law? So to ensure that every element of control measure performs as originally intended and continues to adequately control the exposure of employees. Employers must ensure that whoever carries out maintenance, examination, and test is competent. So what I'll do, I'll leave this here for you all to read. I'm looking at the time because I know the exam question coming out of this sometimes is, what is the duty on the employer? So to break this down, the duty is to follow Schedule 2 then of the COSHH regulation to design, to control emission, to reduce it to the source, whatever have you. Coming out of this, I have seen a question which is, other than the employer, who else have, like a duty to maintain the LEV systems? Have you read this, you're going to see a lot is on the employer, and I guess NEBOSH knows that a bit. But, 2 other persons that have a role to fulfill would be, if you read to the end of it, I know I'm moving it a bit fast, you have, of course, employees, yes, right? So employees, but you also have this slide here. So the heading is on this slide, right? Or the heading is the answer that you also have designers and installers. So that's 2 right there. 2 other persons that have a duty to fulfill for the LEV system. In addition to the employer trying to control, emission at the source, whatever have you, would be the installer and the designer of the LEV system. So I could probably read this one. That's about the end of it there anyway. Right? So section 36(1) says, where the commission by any person of an offense under any of the relevant statutory provision is due to the act or default. Okay, this is actually section 36 of the HSW Act. I wouldn't go on reading it because I know what it have in it. This is just a duty, that if somebody did do something wrong, that they can't be charged. But again, the heading is the answer. 2 more persons with responsibilities, the designers and the installers. Right, a couple of questions, or should I say pictures there. I would be doing a past paper also and putting it up on the system, right? I would also, in the course of this week, I'll have Janet or myself would email the PowerPoints to you all. Did mention that the top here is the best we can. That was the best position to put the webcam, as you know, it didn't have much content up there anyway. Sometimes often it had a blank space there or just some simple content, right? So we'll do the past paper again. Feel free to do your past papers. The office is open 8:30 and 2:30 p.m. Come by, drop your past papers, email your past papers. I'm gonna have a look at it next week. Once you once you do anything, we'll probably come back and look at it right here if the ban is not lifted anyway. We did consider the idea of this Skype session. What I did say though is that for these short delays, like a week or two, I think the videos are useful in that once done, they uploaded, and then you now could look at them in your free time. With a Skype session, you had to be present, you had to be next to a computer, which even for me is difficult to do, right? But with the videos going up on YouTube or on the YouTube channel, you can then look at them at your own time. Please remember to sign in. We would be looking at it and the attendance would be drawn out from those who would have signed. You also need to remember that NEBOSH operates like this. I'm looking at the time, 4 minutes again. That NEBOSH operates like this quite often around the world. We are probably one of the only course providers for a matter of concern where exams are concerned. In fact, is that is something that NEBOSH will have to answer, right? If exams are going to be held in the month of July, we'll have to wait and see. We have had no direct word from them. We did get some items of how to handle people who are ill on the day of exam, which is basically not to handle them, we really refer them to a medical facility. So I'm looking at the time. I have 3 minutes again. I have to cut off. I'll just kind of give a quick review in 1 minute time. The first piece of this lesson was the hierarchy of control, or what we could call it that, but really is Schedule 2 of the COSHH regulation. We look at the different parts of the LEV system. The question coming out of all of this is, how could the system fail? So the answer to the question really is to link it to a part of the LEV system, the hood being of the wrong size, wrong shape, wrong position, the docking material probably being of the wrong material, probably being metallic in a corrosive atmosphere, being square. We look at things like the type of filters. They have to know some names: electrostatic precipitators, wet scrubbers, types of fans, centrifugal and axial, some of the advantages, disadvantage of those. Quite often the advantage is things like cost and efficiency and noise and whatever have you, or even the disadvantage. And the end of it had, how do you measure the effectiveness of the LEV system? A lot of it is that you measure the velocity and the pressure. There are different instruments used for that, typically anemometers for airspeed and manometers for pressure. So I have to sign off. This is the last minute. We wish you all the best. Take care during the course of the week. Take care of yourself and your families. Get some supplies when the window of opportunity is there. Anyway, don't overdo it in the groceries, but get some supplies anyway. And please give me, some comments on this. It is a raw video. I'm not going to edit it. I'm just going to put it just the way it is anyway. No, any mistake would have been talking for an hour anyway. But I'm going to put it up just as is. So stay safe. I'll see you all again. I'm going to upload another one with the past paper, but I'll see you all again when we see again. But please look at the video and put a comment on it. All the best. Bye.